Testing 1, 2, 3. All right, my name is EJ Daigle, again, Dean of Manufacturing here at Dunwoody College Technology. And I'm going to talk a little bit more specifically than just troubleshooting. Well, it's part of the PLC 101 lecture series here, primarily aimed at troubleshooting control circuits. However, the troubleshooting methodology can be applied to troubleshooting almost anything. So. All right, first of all, we'll get into just a little bit of PLC knowledge. I want to get you up to speed a little bit on just, looking at ladder diagrams again and kind of signifying, what are the things that I'm looking at. It's less about, being able to read a ladder diagram or read a relay logic or read a circuit as much as it is just to be able to look at all the detail that you have. So in this case, we're going to answer the following questions relative to the ladder diagram below. So first thing is, what counter is being used. At this point in the curriculum, we've been through one complete platform. We're now starting our second platform. We're getting into troubleshooting, some other things. What are we looking at? Well, it's pretty obvious that what I see here is a CTU, or a count up counter, or an up counter. The next question would be, when is the red light illuminated? So I want to go down and find, where's this red light? Well, here's this red light right here. What you'll notice as I look at this is everything in black from here to here. This appears to me to be the PLC code. Okay. If you look outside of the black, these would be your wired inputs. And on the right-hand side, these would be your wired outputs. And typically, we don't see all of this stuff at once. So the reason why I bring this up is, a lot of times your code resides in your software package, right? This is in the software somewhere. And all you have to look at is perhaps the wiring diagram. So a big set of prints that shows how all the I/O is wired up. This push button switch goes to I2, this push button switch goes to I3, this output screw terminal goes to a red pilot light. But I don't necessarily see how those are interconnected in the PLC code. So I may actually, in addition to working with a set of prints, I may also have to have a laptop computer monitoring the code that's running on a particular controller or something like that to make sense of what's going on. So I want to know when this red light's illuminated. What I'm really looking at is, when is this output instruction O2 on? Well, I can see O2 right here in the software corresponds to my pilot light, and it corresponds to the C50 done bit. So every time this switch 1 increments or makes a 0 to 1 transition, the counter is going to increment by 1. So a 0 becomes a 1 becomes a 2, so on and so forth. So when does the red light illuminate? Well, the answer is when the counter's done, which means the CTU count, or the CTU accumulated value, is greater than or equal to 30. That's when the red light's going to turn on. When is the counter incremented? Well, we kind of already answered that. Every time I press this switch down, I make this go 0 to 1. And then when I release the switch, it goes back from 1 to 0. Each one of those 0 to 1 transitions is going to account for this counter incrementing by 1 place. So what does the incrementing of this thing? Well, it's that switch 1. So every time I press switch 1 down, that's going to increment the counter. And if you're wondering what switch 2 is, well, we can see switch 2 is actually hooked up to a reset instruction that would reset the counter. All right, so let's get into what, how do we troubleshoot? Because I'll be completely honest with you, when we look at this package here, assuming the machine is working correct, your problem is probably not going to reside in the software. So typically the prints are going to give me the wired up inputs and the wired up outputs. And the reason why those are important is, typically wires can come loose, they can vibrate loose, or inline fuses can blow, or somebody may bump into a connector shell or something, an Amphenol or quick disconnect going into a control cabinet, and that may break a pin or something. So typically it's your PLC code is no moving parts. If the PLC is still running, odds are the software is still good. So we typically are going to look at the hardware, look at the software, and look at the hardware again. And in most cases, we may not even have to look at the software. So what makes up your troubleshooting toolbox? I would tell you your three biggest things. We got all these fancy tools, right? We got a multimeter here, digital multimeter. We got a laptop computer. I would tell you more important than those two tools are these tools here: your eyes, your ears, your hands, and a nice good flashlight. Many times you can go into a circuit or begin troubleshooting a system, and you can tell what's wrong by, and I didn't even draw it in here, but I'd also draw in here your nose too. I don't know if that's the best drawing of a nose here, but I've got my nose here, right? My nose. Your nose also can tell you if something's hot. You can touch something. Be careful, to go into the weld shop and start touching things, but you can kind of put your hand next to something, see if it's warm. A lot of times you can hear, mechanical issues like bearings and things like that. Belts might squeak and bearings might grind. You can hear those things. And then, first and foremost are your eyes, getting out a good flashlight and taking a look. I've seen so many times someone grab a computer and hook it up to a PLC, only to discover, oh, by the way, a forklift ran into the side of that control cabinet, and that feeder that's going into there is actually dented or bent, or there's a pin broken inside. A lot of times it isn't necessary to go in and check voltages. Sometimes it's much simpler than that. However, that being said, if it's not something obvious with your eyes, your ears, your hands, then this multimeter here becomes one of your best friends. And if that multimeter isn't telling us a lot, guess what? Then this computer can become one of our best friends too. The computer is essentially a multimeter. The only difference is it's looking at, if you go online with your code, it's looking at a bunch of different I/O points all at once versus going to the meter and checking terminal by terminal. All right, so what are some common PLC faults that you might see out there? Probably one of the most common ones you're going to see is this first one here, is a mechanical problem. We have a lot of mechanical parts. These are the moving parts. So you have limit switches, you have sensors, and over time they vibrate, they come loose, they get banged into. Someone's pulling a cart next to a machine, or somebody's driving a forklift and backs up into the machine. Doesn't do damage to the machine, they don't think anyways, but maybe they knocked a sensor out of alignment. One of my favorite ones is a story from local food company here, that there was an electrician standing up on a conveyor belt changing a light bulb, and he stepped on a sensor that was counting product coming down this conveyor belt. Didn't think he damaged it much, but he kind of bent the bracket it was on, and now the sensor's pointing up and it's no longer aimed at the photoelectric reflector on the other side. And anybody that's ever troubleshot their garage door, you hit the button on your garage door and the garage door doesn't go down and the light flashes. Well, a lot of times that's the safety sensor at the mouth of your garage door that got bumped out of alignment. A great example that I've seen at a local food company here as well. So something getting out of alignment, or a loose limit switch or something like that. I/O wiring problems, it is possible that there's some poor terminations, especially if you're looking at a brand new install and something's not working in your troubleshooting. I've seen everything from, you've got a screw terminal here and somebody wires into that screw terminal. I'll kind of give you some hidden lines underneath here, and it's actually the screw is actually pressing on the insulation of the wire. I always like to, when I go into a screw terminal, I actually like to see that insulation actually is clear, and I can see the strands of the wire going in there. So just so that doesn't happen. This has bit me in the butt before. I also don't want to leave a ton of this hanging out, and I don't want wires going out like this and stuff too. But poor terminations, broken wiring, incorrect wiring, typically this is going to show its head, when you're first installing it or you're making changes to wiring or something like that. I/O addressing, again, this will happen a lot if you're making changes or if you're in a new install where you've got the electrician wiring up per an I/O listing sheet, and the programmer's wiring up per a symbol table or an addresser symbol table, and the two don't match. And so he wires up the start button as input 0, and the electrician wires up the stop button as input 0, and everything's off. This would be more of a programming fault here. Coil conflict, this happens in the lab when you're first learning, but it can also happen out in the real world too with a new program. If we address the output more than once, the PLC is going to write to the data file And you're going to get some corrupt data because it might say in rung 1 the output's on, and in rung 7 the output's off. And the reason why the output stays off is because that's the last thing written to the data register. And so you go to read inputs, execute program, diagnostic communications, update outputs. When we go to update outputs, the last thing written to that register is what's actually going to happen. So we always, we can address the inputs as many times as we want, but when it comes to a coil, we really only want to address that coil, that output instruction one time. Power problems, this is very common. You may have problems with fuses on feeders or disconnects. You might have breakers. You might have power supplies, to the PLC. And some of those power supplies have fuses or breakers inside of them as well. You have I/O modules, an output module that may have a fuse on it, analog problems, voltage problems. The beauty is a fuse or a breaker or whatever these power problems entail, they actually are easy fixes, and for the most part they're easy to find as well. But the thing to be careful on with fuses and breakers is you don't, the rule of thumb is you get one freebie, meaning if I walk up to a panel and there's a fuse blown or a breaker tripped, you get one, what I call one freebie. What that means is go ahead and reset it, turn the machine back on, put it back in its normal state. If it trips again, you've used your freebie. You now need to begin troubleshooting. The reason why I say get one freebie is because you can get a voltage spike across the line. You can get a little bit of a spike or a surge or something like that, and you can't always control those. Those are somewhat intermittent. However, if the breaker trips and you walk up to the machine and you turn it right back on and it trips again, this would be true in your house. This would be true, in an industrial environment. You ought at that point, on that second trip, especially when you turned it on and it tripped right away, you ought to troubleshoot. I wouldn't just keep trying to reset it. Oh God, it turned on this time, because again, the breaker's telling you something. It's telling you there's something wrong. So that's an important detail for you. PLC hardware problems, again, more likely if machines are being moved, or if machines are first being installed, or the machine's being upgraded, modules may come loose from the chassis, you may break a connector, but not typical operation are you going to have these PLC hardware problems. 6-step troubleshooting guide. This is very common. You'll see people, elaborate this in different ways. However, it's the same idea. When you talk about what is the most important, oops, how did I get there? Let me get out of there for a second. There we go. We talk about the most critical step to troubleshooting. If there's nothing else, number one, this is the most important step to troubleshooting. Highlight this in your notes, is symptom recognition. The ability to recognize something that is wrong is the most important. I don't know how many times we've seen operators continue to operate a system, or override a limit switch, or do some sort of cheater method to keep the machine working. They said, well, something's wrong, but rather than reporting it and getting maintenance involved or troubleshooting it, they just kind of make it work. We need to recognize something's wrong, and we need to stop, and we need to let somebody know. So the ability for an operator or a technician or an engineer to recognize something's not quite right, and call it out and stop what you're doing and say, let's do something about this. Step number 2 in the 6-step troubleshooting is symptom elaboration. So this could be, if you're a maintenance technician, or if you're an engineer and somebody calls you up and says, hey, this thing's not running. Well, now it's your job to get out there and collect data. What's not running? What's not working? How do you know it's not working? What does it normally do? How does it normally operate? This is where you really want to rely on those operators. Those operators on the system, they actually have a good knowledge of how the system's supposed to run. So you pay attention to them. It's louder than normal. It's something's wrong, because the fact of the matter is, you can troubleshoot it now with a minimal amount of corrective maintenance, fix the problem and have minimal downtime, or you can wait till you burn up a motor, or you can wait till you tear up a bearing, or you break a shaft, or you break a chain or something like that. So it's important that we work with those people to collect the data. What is going on? Why do you think something's wrong? Give me the symptom. Tell me what you think is going on. Then we're going to list the probable faults. Well, I've got this chain over here, and maybe it's that the chain is not lubricated. Maybe it's that the chain is too tight. Maybe it's that the chain is too loose. What could be causing this to happen? List a list of faults that you think could be the problem. And then from there, we want to start localizing the fault. Localizing, one of my favorite things to do here, especially if it's an electrical fault, or even like a pneumatic or hydraulic fault, is cut the circuit in half. See where you have a signal. So let's say at the output of this thing, right? Way down the line somewhere, I don't have a signal. Way down here, I'm expecting a signal, I don't have it. But up here, I do have it. Up here, I have a 1. Down here, I have a 0. Well, I'm going to cut the circuit in half and see what I have here. If I have a 1 here, I can go this way and continue going until I get a 0. If it's a 0 here, I'll go this way. And I just keep cutting the circuit in half until I find the area where it changes from 1 to 0, or the pressure drops, or the voltage changes, or something like that. We'll go into that one in a little more detail in a minute here. 5 is isolate and replace the component. So once you've determined the fault, if it's something simple like a fuse or a breaker, go ahead and make the repair. Replace the fuse. Reset the breaker. If you've determined that the chain's too loose, tighten up the chain. If you've determined that there's a loose wire, replace the wire or tighten up the wire, tighten it in the termination, whatever it takes to make that repair. And then the 6th step, and one of our important steps here that this is the one that people tend to forget about, is failure analysis and documentation. Restart the system under normal conditions and make sure that your failure is gone. And really, really important is to document your results. Why? So in a lot of cases, you may have a log that you keep, a logbook, or there may be some maintenance manual that includes a place to take notes, or you may have some maintenance software where you're going to record notes on a particular machine. Document those results, because that way the next technician, on second shift or third shift, or 6 months from now, if you don't work there anymore, can look at that and say, oh, well, this has happened before. And if this starts to be a regular occurrence where I'm tightening the chain, every 6 days on this particular machine, is there a different problem? Is there a different way we could fix this so we're not constantly doing the same thing over and over again? All right, so those are kind of your standard 6-step troubleshooting steps or guide. Now I want to get into, you can actually use those steps in these other troubleshooting methods. However, these are some other methods. So troubleshooting by substitution. Troubleshooting by substitution is the process of replacing suspect components, either one at a time or in small groups until the fault disappears. So imagine you have a modular system, and you have a rack of modules here, right? And you don't know which module it is. They're all plugged into a rack here. Boom, 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 boom. And there could be 50 of them. There could be 60 of them. You might say, you know what? I'm going to replace this one, and this one. And I'm going to recheck for failure. Failure goes away, then I know one of those fixed the problem. If the failure doesn't go away, I'm going to put those modules back in and then replace this one, and this one. If the fault goes away, great. If the fault doesn't go away, I'll put those back in. I'll continue down the line. I don't like this as a troubleshooting method. It's sort of like throwing darts and hope that you hit the right module. I will tell you, in my work on nuclear submarines and military applications, where we had a lot of Type 2 quick change modules, we had to make repairs quickly. In a time of war, you don't have time to sit down and troubleshoot for a half an hour. Or if you're in a system where every hour of machine downtime equals $10,000 of lost money, it might be cheaper and more efficient to go ahead and replace 3 quick modules, or make the troubleshooting simple by replacing modules quickly, because even though you're replacing a lot of modules, that might be cheaper than the $10,000 of downtime. So there's reasons why you might do that. The other thing I don't like about this one is I don't like the idea of yanking out good components and then putting them back in. So I pull 3 components out, put in 3 good spares, find out that the good spares didn't change anything. Do I take those good spares out and replace them back with my original components? Well, now if these components have connectors on them, wires on them, you only get a certain amount of times that you can plug a module in and out before you're actually going to insert other problems into the system. The divide and conquer method. This is another troubleshooting method. I love this method. So again, we talked about this a minute ago, right? Let's say that I have a DC source here, 24 volts, and I'm just going to draw a circuit. I'm not gonna be real picky about this, right? But let's say that I've got 3 loads or 3 things that are consume the voltage, and normally I get 8 volts here, 8 volts here, and I get 8-volt drop here. So I consume all 24 volts. So if I call this, let's say ground right here, this is my 0-volt reference. You know, if I go here, normally I'd expect to read 16 volts from here to ground. And if I went here, normally I'd expect to read 8 volts from here to ground. Now let's say our circuit's not working, right? What I might do at that point is go ahead and decide, well, I'm going to go look and see if I can find, let me grab a different pointer here, different color. All right, I'll do this in blue. So now I'm going to say, you know what, I'm going to go, and I know something's not working. You know, the tech said, something's not working. So I go ahead and I go to this point where I know that I normally would read 16 volts. And all of a sudden at this point, I read 0 volts. So interesting here now, right, is where does that fault reside? If you read 0 volts here, normally you expect 16 here, right? If the circuit was open here, right, I would expect to read what? I would maybe expect to read source voltage up here, 24 volts, right? Because I have infinite resistance on this side of it. So now I'm going to go this way, or I'm going to go this way. Well, I will tell you, if I'm reading 0 volts there, you know, at this point, I'm kind of guessing that maybe the open is here, but I also could be shorted here, right? So I'm going to take a step over to here, where I normally would expect to read between this point and ground. I would expect to read 24 volts. And so now I read 24 volts here, and I read 0 volts there. What does that tell me? I have 24 volts of potential there to 0 volts of potential here. That tells me there's an open in between here and here. But by breaking that circuit in half, and when you're talking about 3 resistors, no big deal. But what if you have several components, right? Or not even resistors. Think about junction boxes. You know, a wire comes into a junction box, comes out, goes over to another junction box, comes out, goes over to another junction box. I might be able to break, you know, and go somewhere else, go somewhere else. You know, this is my source over here, VS. You know, and maybe I have a load over here that I'm expecting to do something. I might be able to go into this J box here and actually look and say, okay, do I have voltage here? I do? Okay, let's keep going. You know, and see where I don't have voltage. And I can just keep working towards the sink, towards the 0 volt source, or towards the source or to the sink based upon what I'm actually reading. So that's going to be an important troubleshooting methodology there. Other troubleshooting methods, forcing I/O. One of my favorite things to do if I'm really struggling and it looks like the wiring's good, everything appears to be working well, I can always go into the software and look at the status of the I/O. And I can always do things like force a bit on. You know, I can right click and force a bit on. I need to enable my forces, force the bit on, and when I force that bit on, I'm actually now taking whatever's in this source and putting it in this destination. Now I can look and say, is that in that destination? If it is, great. If it's not, then maybe there's a different problem. But my guess is that what I've really done is I've taken whatever this hardware piece was, this I:1/0. I've taken it out of the circuit. And I've said, you know, software, go ahead and try it. So I know my software is working, and I know I don't have maybe some other file that's overwriting what I'm trying to do with this instruction. I know that the software works, and maybe it's the switch itself. Danger on this one, make sure if you use forces, you gotta remove them. You gotta disable them upon completion of testing. The last thing you want to do, you know, is have the Yoplait yogurt line at General Mills have forces installed on it, right, as it's running, because now the sensors that are supposed to do something are being overridden by a software force. Okay. The other term that we use a lot on the hardware side is what we call flagging. So in software, we call it forcing. In hardware, a lot of times we'll call it flagging the I/O. So maybe I have a sensor, right? In this case, I've got this nice limit switch down here. And maybe this limit switch is on a guard that goes in front of a machine. And for whatever reason, the operator's trying to run the machine, it's not working. I might think, well, you know, is it something to do with this switch down here, this limit switch? So I might go down there and I might manually actuate this limit switch by pressing down on it. And I could do that in some cases, small limit switch. I might be able to do that with a finger. I might be able to use it with some sort of override tool. If it was let's say it was an inductive sensor, I've got a little inductive proximity sensor right here that's sensing metal. I might be able to put like an adjustable wrench next to it, and I can look for indication then on my PLC. I might even have to have somebody at the PLC on a two-way radio. And I say, okay, I'm going to activate the limit switch. Go ahead and take a look at input 6. Does the LED on the PLC turn on? Yes, it does. Great. Or I'm going to put a wrench near this sensor. And I'll see the sensor actuate, because usually these sensors have a nice little LED on them up here somewhere. On the two-way radio again, is input 12 turning on with that sensor? Yes, it is. Or no, it's not. Maybe the sensor's working fine, but maybe there's a broken wire leading up to the input. So lots of things that can go wrong there. Some other troubleshooting methods. One of my favorite ones here, when you get into a lot of your machine manuals, so you've got some equipment manuals, engineers will typically, they'll try to create what I call fault isolation trees, or FITs. So if there's a common fault that might happen, they might create a fault isolation tree in the manual to tell you how to overcome that fault. So common faults can be easily diagnosed with fault isolation trees. These block diagram procedures allow operators or junior technicians to quickly diagnose common problems. You'll actually see this if if you call your cable company on the telephone. The people on the cable company, in fact, a lot of that's automated now. It's actually an automated fault isolation tree. But if you get to where you're talking to somebody on the phone, they'll ask you a question like, okay, is the green light on your cable box? Yes, it is. Okay, go ahead and unplug it, plug it back in. Did the green light turn on again? They'll go through this fault isolation tree, and it'll do one of two things. It'll either fix the problem, or it typically ends in, we got to send a guy out to take a look at your cable box, right? So in this case, you see stuff like this. Is the fault indicator lit? Yes. Replace the part. Is the fault indicator lit? No. Does the system boot? No. Run a post. Does the post fail? Yes. Replace the part. Does the post fail? No. It goes through this sequence of all these steps, and then it'll tell you, oh, you may want to do this, or, oh, you've got a software problem. Or in some cases, it could be as simple as, oh, the fault has been corrected. A lot of times this replaced part will end up in, did this solve the problem? And then fault corrected, right? So there's these nice trees that they create for what I would call common problems that you might have with the machine. Unfortunately, most problems are not common, and they become, this is the reason why we pay technicians and engineers and folks like that a lot of money, is because we can't always solve it with the standard fault isolation tree. For the stuff that's easy, works great. And a lot of times a fault isolation tree will reside in the hands of an operator. It doesn't even necessarily need to hit a technician or an engineer. Intermittent faults. This is by far the most difficult type of fault to troubleshoot. What intermittent means is it means a fault that isn't a hard fault. So you can imagine, your car, the check engine light turns on. And nowadays, check engine lights are smart. They can actually log what they've done and things. But, in cars from 10 years ago or so, a check engine light would turn on, and maybe you'd drive to the dealership, and by the time you got to the dealership, the check engine light turned off. And the technician would tell you something, well, I can't troubleshoot it if the light isn't on. Or you hear a squeaky noise on your car, you drive it into the shop, and the technician turns it on and it doesn't make the noise anymore. So these faults tend to come and go, and they are typically hard to troubleshoot because you don't have a hard fault signature. And a lot of times you begin troubleshooting and the fault goes away. So, another thing about them is they typically show up at inconvenient times. Then when troubleshooting begins, they may disappear. I will tell you, when you're looking at intermittent faults, what you want to do is when you get the fault, you want to begin troubleshooting. Document every step you've taken to troubleshoot that intermittent fault. If that fault disappears while you're troubleshooting, fine, stop. But the next time that fault recurs, assume, well, you never want to assume, right? But assuming all the indications are the same, then go ahead and start where you left off from the last time that you troubleshot. Because if you begin troubleshooting from the beginning, it's very possible, you've gotten 6 steps into troubleshooting and the fault will go away again. So if you restart every single time, that can be problematic. The other thing I've seen people do is use things like there are digital multimeters, there's digital storage scopes, there's different digital test equipment that you can actually hook up to a circuit and have it log data. So you could put it onto a circuit and take a voltage reading, every 30 seconds or something like that. So you might discover that, oh, you know what, at 2 o'clock in the morning every night, we get a little surge in electricity, or something happens that maybe is causing this because it's lining up perfectly with what's going on here. You'll also see gauges. Sometimes you'll see analog gauges, like if you're reading pressure, and the pressure gauge, reads like this. They sometimes will have little needles on them that'll show the min and the max. And if the needle pushes too far, it'll actually push this little needle over, so you can see how much distance it traveled over. So anything you can do to kind of see what happened may be beneficial in troubleshooting. All right, some basic troubleshooting knowledge questions that I think are really important for you to understand at this point. All right, so question. A normally closed limit switch is wired to a PLC input, and the limit switch has not been actuated. How could you quickly verify the limit switch and associated wiring is working correctly? So we've got a limit switch. I'm going to go over here. We've got a normally closed. So it's going to look something like this. I got it drawn kind of backwards here. There we go. So normally closed limit switch, as I press it down, it would open, right? But it's wired up to my PLC input. And how could I verify this? Could I press the limit switch and verify the PLC indicator extinguishes? Because normally the PLC indicator would be on because it's normally closed, right? So when I press it down, it'll open up. And then that PLC indicator should be on when it's closed, and it should be off when it turns. Sure, I could absolutely do A. I'm pressing it and verifying the indicator on the PLC for that input. How about B? Let's take a look at B here. B says, could I press the limit switch and verify no voltage at the screw terminal? Could I take a voltmeter, and put it here, and then put it to 0 volt, and verify the voltage is present, and then when I press it, it goes away? Absolutely, you could. That's essentially the same thing. On this particular one, you're trusting the indicator, and this one you're using a voltmeter. And it may be possible that maybe you're not dealing with a PLC. Maybe it's just triggering the coil on a relay. In this case, the voltmeter might be the better tool. Could I monitor the input status by going online using a PC, a programming cable, to verify the signal at the limit switch is pressed and released, or verify the signal as the limit switch is pressed? Absolutely, you could. I would say, as far as order, I'd probably do this one first, this one second, this one third, depending on the situation I'm in. But the answer to this is any one of those would tell me if that limit switch is working right. It's going to give me a visible indication of whether that limit switch is providing voltage to the input or not providing voltage to the input. All right, another question here, troubleshooting knowledge. The input-output listing sheet is provided. The input-output listing sheet provided to, I should probably say is provided to document the entire logic program as it relates to the inputs and outputs of the machine. What do you think? Absolutely not. It says nothing to do with the program. The logic of the program is not on the I/O listing sheet. Okay. The I/O listing sheet deals with the field devices, the field device inputs and the field device outputs. So I'd say a negatory on that one. Is it B? Does it show how inputs are connected to outputs? Well, on a PLC, if you think about a PLC controller, the physical inputs are not connected to the outputs. Remember, what connects the inputs and the outputs, really is the program in here. So the inputs are just connected to screw terminals, the outputs are just connected to screw terminals. So absolutely not on that one as well. That doesn't even make sense. Does it show how the PLC program is compiled? What the heck does that even mean? How would the I/O listing sheet show how the PLC program is compiled? I don't care how the PLC program is compiled. I know that compiling will tell me if there's any errors. It'll check for things that are missing. You know, it'll turn it into the code that the PLC needs to run, but the I/O listing sheet has nothing to do with that. Or is it D? Does it document the physical connections of the PLC to the machine? Absolutely. So the I/O listing sheet documents how field devices are connected to the PLC. Basically, how does the input devices connect up to the input terminals? How do the output devices connect up to the output terminals? A lot of times it'll also show how the motor starter is wired up. It'll show how the overloads might be wired up. The PLC power itself might be wired up, but we're talking about the physical wiring connections is what the I/O listing sheet gives us. Another question here. Which of these would be considered the first step in troubleshooting a PLC? All right. Let's see. Test field devices? Probably not. Is it a field device? I don't even know. Maybe it's a power thing, right? Test wiring? No. Check input and output? No. We want to identify faulty operation. Now that's a different way of saying what we had back here, right? So it's a different way of saying symptom recognition is what it is. So you see here we've got symptom recognition. Symptom recognition is, symptom recognition, I'm kind of scrolling through my slides here too quick. Symptom recognition is the ability to identify faulty operation. So with that would conclude the 13 slides I had here for the troubleshooting sequence of this. I appreciate your time. Thanks.